Now, these are all uses of what we'll call our fundamental counting principle. The book calls it the product rule for the obvious reason. The product rule says in a string of length k, we're always going to use k for the length of a string. We'll use it in slightly different contexts elsewhere, but we'll try to keep k, the letter k, to be used for something that's like a length. If the ith term can be filled in a particular number of ways, n sub I, and this number of ways to fill the ith term doesn't depend on how any of the other terms, or in fact all you really need to know is it doesn't depend on how any of the previous terms have been filled, then the total number of possible strings is just the product, n1 times n2 times n3 up through n sub k. This is the product rule. This is exactly what we were doing, if I go back here, in computing the number of ways to get a California license plate of standard form is just 10 times 26 times 26 times 26 times 10 times 10 times 10. 10 is the number of ways of filling the first position, 26 for the second, 26 for the third, 26 for the fourth, 10, 10, and 10. So these are all examples of this general product rule. And the product rule can apply in lots and lots of different situations, which we'll be coming across in the future. Can we prove that this product rule works? Well, again, let me remind you, as I talked about in the previous video lecture, you won't be required to write down any formal proofs, but the proof of this product rule is really not very different from the proof of the result in standard problem number 1. It can just be done by induction. If you just assume that for each position, I equals 1, I equals 2, I equals 3, etc., for every value of I, the number of ways of filling that ith position is precisely n sub I. If you take those all as a given, then we just want to prove by induction on the variable k, which represents the length of the string here, we want to prove by induction on k that the number of ways of producing such a string is this product, n1, n2, n3, up to n sub k. So the answer is we can prove it by induction in a manner just like we did before. I'm not going to write the formal induction proof here, but I'll just tell you basically how it works. And if you would like some practice in writing down a formal proof, try to write the details on your own of how you would fill out a formal induction proof. Remember, there are 2 steps for the induction proof. You want to start with the base case, in this case the k equals 1 case, meaning a string of length 1. You want to produce a string of length 1, and you can fill in that first entry in n sub 1 ways. Well, how many ways can you do it? N sub 1. And that's exactly what this product would look like when k equals 1. You only have that first entry, n sub 1. Then you want to do the induction step, which says, which works like this. If you assume that for some value, or that for any value of k, just pick a value of, let k be arbitrary, some number greater than or equal to 1, assume that this statement we've written here, the product rule, holds for that value of k. So assume that's true. Now try to show that it holds for k plus 1. In other words, if you know strings of length k, that there are n1 times n2 up to nk ways to produce a string of length k, then you want to show that there are n1 times n2 times n3 up to n sub k times n sub k plus 1 ways of producing a string of length k plus 1. Well, how would you show that? Think of the last element, this k plus first entry. Kind of ignore that for a minute. There are n1 times n2 times n3 up to n sub k ways of producing the first k, of choosing the first k elements in your string. And then you can put in the first element for the last one, or the second element, or the third element, all the way up to n sub k plus 1 possible different elements. For each of those choices for the last element, you have this product up to n sub k ways of choosing the first k entries. Put that all together, try to write down the formal proof, and you'll see that the product rule can be proved by induction just like we did before. And that means these results for counting license plates really do work out exactly as we computed. So before we finish today, we want to talk about standard problem number 2 in the book. Standard problem number 2 asks us to find the number of strings of a given length k that use elements from a given set of size n, where no element appears more than once. So we're not allowed to repeat elements. In general, for a string, you can repeat elements. But here we're asking, what if we're not allowed to repeat elements? We want a string of length k from an alphabet or set of size n. How many ways can we do that? Well, here's how I like to do this. Let's say we have a string of length k. I like to represent that with a bunch of dashes here. I'll put k dashes. Of course, we don't know how big k is, so I'll put the dot dot dots here. Think of this as length k. And we have a first position, second position, third position, all the way to a k minus first position and a kth position. How many ways can we pick an element for the first position? Well, I'm going to write down here the number of choices. Remember, our alphabet or set is of size n, so we have n different letters or elements from our set that we can put in the first position. How many choices do we have for the second position? We might think we can just use any element again, but we can't use the same element that we used in the first position, so there are really only n minus 1 choices for that second position. And remember, I'm just putting the number of choices here for each position. What about for the third position? Well, there are no repeated elements allowed, so we've already used 2 of the elements. There are only n minus 2 left, so we only have n minus 2 choices for that third position. And then you see we have n minus 3 for the next one, and we keep going until we get to how many at the end? Well, you'll see this is n minus k plus 2 and n minus k plus 1. This can be tricky. Why is it n minus k plus 1? Just look in your head. What if it were a 2 string of length 2? You would have n choices for the first one and n minus 1 for the second one. That would be when k equals 2, you'd want that to be n minus 1. If k equals 3, you'd want this to be n minus 2. It's going to be n minus k plus 1, and the one before that is n minus k plus 2. You could also write this as n minus the quantity k minus 1, because there are k minus 1 spaces ahead of you, and you can't match any of those letters. And of course, n minus the quantity k minus 1 is the same as n minus k plus 1. So the number of strings where no element appears more than once is just n times n minus 1 times n minus 2 all the way up to n minus k plus 2 times n minus k plus 1. It's this product. And let me show you a common way we'll write this. That's the answer, and that's the answer to standard problem number 2. Let me get rid of that. In order to write that nicely, let's remember that when I write n factorial, with an exclamation mark there, that means n times n minus 2 times n minus 3, and you keep going all the way to 3 times 2 times 1. You go from n all the way down to 1. So you have this product of numbers. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. You should become familiar with the different factorials. Now, of course, another way to write n factorial, let me write it like this. K factorial is just k times k minus 2 times k minus 3, all the way up to, I'll just write 2 times 1 there. This number here that we have, which is the answer to standard problem 2, I'll write here, that's equal to n times n minus 1 times n minus 2, all the way to n minus k plus 2 times n minus k plus 1. And if I kept going to n minus k, n minus k minus 1, and all the way to 3 times 2 times 1, that of course wouldn't be the same as this answer that I want, because I added stuff there. But if I divide out all the stuff that I just added, which is n minus k times n minus k minus 1, all the way to 3 times 2 times 1, that really is the same as this answer to standard problem 2, because all of this stuff here cancels, and we're just left with that answer. Well, the numerator here is exactly n factorial. The denominator is now, I didn't want k factorial there, I want n minus k factorial. So the answer to standard problem 2 can be written as n factorial over n minus k factorial. Note that this will only make sense, even here and down here, it only makes sense if k is less than or equal to n. Why? Because if k is bigger than n, you're going to get down here all the way down to 0, and you'll just get 0, that saying this is impossible to do. But of course, it should be obvious that it's impossible to create a string of length k if k is bigger than n, using elements from a given set n with no repetitions. If the number of positions in your string is larger than the number of elements in your set, there's going to be a repetition somewhere. Also note that if k equals n, what you get here is exactly n factorial. Down here, you wouldn't have anything in this part here or in this part here. So by convention, to have all of this make sense, we say 0 factorial is exactly 1, and then this result works just fine when k equals n. We'll be continuing with problems like this in the next set of lectures.